You can't get there from here, not because there's nothing there. We've found thousands of planets now, some of them sitting in the right place around the right kind of star, with the right temperature for liquid water. The universe is littered with potentially interesting places. The problem is the distance. Let me give you the number first because you need to feel it before you can think about it. The nearest star to our sun is Proxima Centauri, 4.25 light years away. That sounds modest, until you understand what a light year actually is. Not a unit of time, a unit of distance. The distance light travels in 1 year. Light moves at just under 300,000 kilometers every single second. In 1 year, it covers about 9.5 trillion kilometers. To the nearest star, you multiply that by 4.25. You get roughly 40 trillion kilometers. Now here's something to hold next to that number. The farthest any human-made object has ever traveled from Earth is Voyager 1. We launched it in 1977. It has been flying continuously without stopping for nearly 50 years. Right now it's about 23 billion kilometers out. That sounds like a lot, and it is for us. But it's less than 0.1% of the distance to the nearest star. Voyager has been flying for half a century, and it hasn't even started the journey. That's the raw problem. But the number is just a symptom. The real issue is what physics does to anything that tries to cover that distance. Start with energy. Say you want to send something to Proxima Centauri in a reasonable time, a century, not 1,000 years. To cover that distance, in 100 years, you need to move fast. Not impossibly fast by the standards of physics, but genuinely fast, roughly 1% of the speed of light. Now how much energy does that take? Pick a modest spacecraft. Not a crude ship with life support and food and medicine, just a small probe, the kind you might send ahead to look around. To push even something that small to 1% of the speed of light, you need an amount of energy that is staggering. We're talking about a significant fraction of what the entire human civilization produces in a year just to get a small probe up to speed, and then you need that much again to slow it down when it arrives. And again, if you want anything to come back, now make the ship bigger, because a probe can't do much. A crude ship with everything humans need to survive for a century, food, water, medicine, shielding, power generation, weighs tens of thousands of tons at minimum. The energy requirement scales with the mass. You're now talking about energy budgets that dwarf anything human civilization has ever attempted for a single ship, one way, and I haven't even gotten to the hard part yet. Because here's what Einstein worked out, and what every experiment since has confirmed without exception. The faster you go, the harder it gets to go faster. Not in a simple linear way. It gets harder in a very specific way that gets more brutal the closer you approach the speed of light. The energy required diverges, grows without bound. To actually reach the speed of light with any object that has mass would require infinite energy, and the universe doesn't have infinite energy to lend you. The speed of light is not just fast, it is a hard wall built into the structure of space-time itself. This isn't like the sound barrier, which looked like a wall and turned out to be an engineering problem. We broke the sound barrier in 1947. The light barrier is categorically different. It's not that the engineering is difficult, it's that the physics forbids it. No amount of ingenuity changes the structure of space-time. So you can't go light speed, you can approach it 90%, 99%, 99.9%, and at those speeds something genuinely strange happens with time. I want to be clear that this is not science fiction. This is measured in laboratories and built into our technology right now. Particles called muons are created in the upper atmosphere when cosmic rays hit. They decay very quickly, so quickly that by every ordinary calculation they should disintegrate before reaching the ground. They don't. They reach the ground because at the speeds they're traveling, their internal clock runs slow relative to ours. Not metaphorically, literally. Time passes differently for them. We measure this. It agrees with Einstein's prediction to extraordinary precision. GPS satellites have to account for this effect continuously, or the position errors would accumulate to kilometers per day. Relativistic time dilation is an engineering constraint, not a thought experiment. So here's what that means for your interstellar ship. If you get to 90% of the speed of light, which would require enormous energy, time on the ship slows relative to Earth. A trip that takes 100 years by Earth's clock might only feel like 40-some years to the crew. That sounds helpful, but think about what it means for the civilization you left behind. You leave in 2025. You arrive at a nearby star system, a century later by Earth time. Your crew is middle-aged, they've experienced only a few decades. But everyone they knew on Earth is dead. The world they launched from has gone through generations of change. If they turn around and come back, they return to an Earth that's 200 years past the moment they left, filled with people who have no personal memory of them. The knowledge they gathered on the trip, the experience, the observations, they can radio at home, but radio waves travel at the speed of light, so by the time the message arrives, another generation has turned over. This isn't a solvable engineering problem. This is what relativistic travel does. It severs you from your civilization, even as it moves you through space. And even setting aside the time dilation, there's a second wall people don't think about enough. Space looks empty. Between stars it mostly is, but there are hydrogen atoms floating out there, about 1 per cubic centimeter on average. At the speed you walk through a room, they're irrelevant. At 90% of the speed of light, they aren't. At that speed, your ship is slamming into those sparse atoms with enough energy that the collision looks, from the ship's perspective, like a continuous blast of high-energy radiation. The interstellar medium becomes a radiation environment that would kill humans in hours without extraordinary shielding. Shielding means mass. Mass means more energy to accelerate. More energy means more fuel. More fuel means more mass. The problem feeds on itself. There's also a simple principle. Tsiolkovsky's rocket equation, worked out in 1903, that says the fuel you need grows exponentially with the speed you want to reach. You want to go faster? The fuel requirement doesn't double, it multiplies. For the speeds we're talking about, you end up in a situation where virtually your entire ship has to be fuel, leaving almost no room for the payload. This is why people propose antimatter propulsion, which is the most energy-dense fuel theoretically possible. The problem is that we currently produce antimatter in quantities so microscopic they're almost comic. Enough to fuel an interstellar mission would require a production scale that, compared to what we can do today, strains the imagination past any reasonable engineering projection. Now here's where this becomes a story about civilizations, not just ships. Fermi asked a question at lunch in 1950. Where is everybody? If intelligent life is common in the universe, why haven't we detected any signals? Why hasn't any civilization shown up? This question gets treated as a deep mystery with exotic solutions. Maybe life is rare, maybe they're hiding, maybe they all destroy themselves. Those might all be true, but I think part of the answer is more fundamental than any of those scenarios. Think about what civilization actually requires. Not technology alone. Civilization requires accumulated knowledge passed between generations and specialists. It requires feedback, someone checking your work, building on your foundation, correcting your mistakes. It requires trade, not just in goods, but in ideas. All of this depends on communication that is fast enough to allow response, fast enough that a question can receive an answer within a human lifetime, fast enough that a discovery in one place can influence work happening somewhere else. We kept the Roman Empire together across thousands of kilometers using horses and boats. A courier from Rome to its edges took weeks. That was barely fast enough. It required enormous administrative infrastructure just to compensate for the communication delay. And even then, the empire was perpetually on the edge of fragmentation. Now replace weeks with years. Not because we've regressed technologically, because the nearest neighbor is 4 light years away, and light itself takes 4 years to cross that gap. A civilization at Proxima Centauri, assuming one existed, sends us a message. We receive it 4 years later. We reply. They receive our reply 4 years after that. The fastest possible conversation has an 8.5-year round-trip lag. Not inconvenient. Civilizations scale different. No shared project, no collaborative science, no meaningful cultural exchange can operate across that delay. You would send knowledge like messages in bottles and hope someone reads them eventually. Now push outward. Most stars in the galaxy are not 4 light years away. They're hundreds, thousands, tens of thousands of light years away. We've been sending detectable radio signals into space for about a century. The bubble of space that's had time to receive those signals and send back a reply we could have received by now has a radius of 50 light years, roughly 2,000 star systems. That's a tiny, tiny slice of the galaxy. We've been announcing ourselves for 100 years, and we've barely whispered into the room. The galaxy is 100,000 light years across. The vast majority of it has never heard from us. The absence of a reply tells you almost nothing about whether anyone's out there. And physical travel. At the scales we're actually talking about. A civilization 1,000 light years away which is still a modest distance in galactic terms, takes over 1,000 years to reach, even going fast. The crew experiences something less than that due to time dilation, but Earth experiences more than 1,000 years while they travel. The civilization that launched the ship is unrecognizable. The civilization they're heading toward has had 1,000 years to change since the signal that first told you it was interesting. When they arrive, they're not ambassadors of their civilization. They're artifacts of it. Now I should address what everyone always brings up at this point: faster than light travel. Wormholes. Warp drives. General relativity, our best and most precisely tested theory of gravity, does permit, purely mathematically, certain configurations of spacetime that might, in principle, allow apparent faster-than-light movement. A physicist named Alcubierre described one in 1994. Wormholes appear as valid solutions to Einstein's equations. Here's the honest situation. These mathematical solutions all require something called exotic matter, material with properties, particularly negative energy, that we have never observed, and that there are serious reasons to think may not exist in macroscopic useful quantities. The energy requirements involved are not just large, they're on scales that make our interstellar fuel problem look trivial by comparison. We have never produced exotic matter. We don't know if we can. There are strong theoretical arguments, not proofs, but serious arguments, that quantum mechanics will always destabilize the very structures that would make these shortcuts work. Mathematical existence is not physical existence. General relativity's equations permit many things. What they permit and what the universe actually allows are not always the same question. I can tell you these ideas are mathematically interesting. I cannot tell you they represent achievable physics because the evidence for that does not exist. So we return to the universe as it is. The universe is 13.8 billion years old. Planets have been forming for most of that time. If life arose elsewhere and we have no way to assess the probability, well, we genuinely don't. Some of it may have arisen billions of years before life arose on Earth. A civilization that had billions of years to develop and spread, even at slow sublight speeds, could have colonized large fractions of the galaxy in that time. The galaxy is big, but it's not infinite, and even slow expansion compounds. We see no evidence of this. No stars obviously being dismantled for energy. No signals we've decoded. No visitors. The explanations are many, and the honest answer is we don't know which is correct. But the physics I've described suggest one contribution that doesn't require exotic assumptions. The universe makes connection hard, genuinely hard, not engineering hard, structure of reality hard. The cosmic speed limit isn't an arbitrary rule. It's rooted in the same physics that makes causality possible, that makes it true that causes precede effects, that you receive the letter after it was sent, that the future follows the past. If information could travel faster than light, you could construct scenarios where you receive an answer before you ask the question. Causality would collapse. The universe appears to care about causal order, and the price of maintaining it is that nothing, no object, no signal, no information can outrun light. Civilizations form in pockets. They shout into the dark. The shouting travels at the fastest speed the universe permits, and mostly it goes unanswered, not necessarily because no one is there, but because the universe is so large, and the permitted speed so finite, that the shout and any possible reply may never overlap within the span of any civilization's attention. 4¼ light years, 0.1% covered in 50 years of continuous flight. That number sits differently now than it did when we started.